let's begin. All right, we are on page 34, and we had a couple of people that were absent last time, so we're going to remind ourselves of the problem that we started last class. I'm going to go all the way back to Katrina for this number 1. Okay, let's pause right there. So we got Fred swimming against the stream. How far does he have to go? He needs to go 10 miles to get to his sweetheart. How fast is the current going against him? It's 5 miles an hour against him. And what we're trying to do is not minimize the time it takes, but rather minimize what? The energy it takes. That's the goal, is to get Fred there with as little energy burned as possible. And so we ended up taking a look at this, whoopsies. We ended up looking at this function here. And it turned out that if v is the velocity, then that formula right there, that function, tells you how much energy he burns in making the trip. And so we saw that, for example, if he goes at 6 miles an hour, then he will burn 1,404 calories in the whole trip. In the next row, if we're going 7 miles an hour, do we burn more or less than 6? Burn a little less. Instead of 1,400 calories, we're at 1,100 calories. If you go 8 miles an hour, is that better or worse? Is that more or less calories? It's less, but not by very much, right? I mean, like 1114 to 1109. We're not talking a big change here. And then we start to get into trouble, because if you swim too fast, then you can see that the calorie usage starts to go up, because even though you get there quick, what's true if you're swimming fast the whole time? You're going to be tired. It's a lot of energy at every moment of this trip. So, so I think that we played around last time, and we typed this function into our calculators. So if it's not still there, then I'd like you to type it in. But for some of you guys, I'm guessing it's still there. So calculators out. Make sure that that formula is typed into the y equals. And once you've got that typed in, we thought about our window. I've got a window here projected on the right-hand side of the screen. So if you guys can change your window to those numbers, then we'll all be looking at the same picture. And once you've got your y equals, and once you've got your window, if you hit the button that says graph, you should have a picture like the one that's also projected. That part looks okay. I know you do have the right window. Here, you got to change that to these numbers here. See on the right-hand side, x min is 5.
Oh, kind of.
Oh, well, closer. Okay, do we have a picture? That's good, that's good. Andy, it's good. Tyler, how does it look? Wonderful. Katrina, good. It's this formula right here. So it's 6.5 x cubed is what we had, 6.5 x to the third divided by, divided by x minus 5. Careful to put parentheses around the x minus 5. Just like that. Technically you don't, but it's safest to put it in. Parentheses around the top, parentheses around the bottom. But I think it's okay as it is. And then the window, maybe you can change that window to agree with the one that's over there. You see it says x min is 5. Yeah, so change those numbers. Ben, that's good. Joe, it's good. Serge, do you have it? Change your window to the numbers that are up on the board here. Hazen, that's good. Sam, can I see? Wonderful. Megan? Good. All right, what's happening over here? Okay. All right, so I think just about everybody's in the same place. And the picture that we have is that one that's up there. And so, so you can see that something's happening. So first of all, on the horizontal, what does this represent? What was our x? Our x was really the v, which is velocity. Okay, so the horizontal is the velocity. Now what is the vertical? It's the number of calories. It's energy. So we'll go ahead and label down here. The vertical axis is E, which was measured in calories. And the horizontal axis was our V, which was measured in miles per hour. And so if Fred is looking at all the possible ways that he can make this trip, all the possible speeds that he can make this trip, I'm hoping that you guys can see where the winning point is. If I want to minimize the number of calories I use, do you guys see the point on the graph? Can you put a dot on the point on, like maybe you could copy this graph on your paper real quick. Just a rough sketch, just copy what you see up on your paper. Doesn't need to be super accurate. And then once you've got that, see if you can put a dot on roughly where the minimum point is. Where will Fred expend the minimum amount of energy? What am I looking for on the graph to find the minimum energy point? Where will I find it?
Place where y is.
We're at the lowest. We want to go down to the bottom. So we've got this whole, we've got all these points to choose from, and you want to pick the one that is as low as possible. And it looks like somewhere in there-ish. And it looks actually flat in there, so maybe there's a whole bunch of points that are tied. I'll tell you that if we zoom in, we'll see it curve. I mean, it's not flat at any point there. It's just because there's so few pixels that we can look at. But anyway, the minimum point is someplace in there. This number is 5, 6, 7, 8, 9. What does it look like roughly the best speed is? 7, 7.5, 8, somewhere in there. So at the moment, we can at least say roughly he should be doing something between like 7 and 9 miles per hour. But we want to know more precisely than that. We want to give Fred good directions here. So here's how we do it. On the next page, it talks about some new calculator technique. I want you guys to learn how to use the technology, and here's a new trick that's going to be in our toolbox. So part G, can we go to Tyler to read for us? Part G on the top of the next page. Yeah, right there. You can read them one at a time for us. Okay, let's pause there. Everybody hitting second and then calc. And then you can see a list. Some commands are familiar to us. There's a new one that we're interested in, and it's minimum because we're trying to find the minimum energy point. So we hit 3. Go ahead, Tyler. Okay, so right now my cursor is moving left because I hit the left arrow, and all you need to do is hit this button left enough times so that the cursor is eventually left of the answer. Now it's possible that it's already left of the answer, but I feel better safe than sorry. So I really put it left of the answer. So just hit the enter key, sorry, hit the left arrow a bunch of times until the cursor is clearly left of the bottom point, and then hit enter. Tyler? So we'll hit the right arrow a bunch of times until we get past the bottom point. And I messed up, so I'll try it again. 3. Okay, so we had left bound, enter, right bound. We just hit a bunch of times until we get past the bottom point. And we'll hit enter. You guys see I'm nowhere near the button that says tangent, right? All right, I'll do it over here. Okay, second, calc 3. Left bound. Turns out there's a better way. So maybe it's good that that this is so challenging for me up here, because then I can show you the better way, and now there's actually a reason to use it. But you move the cursor to the right until you are right of the bottom point. That right there is definitely past the bottom point. We hit enter. Tyler? So they'd enter one last time. It does some thinking. You can see in the top right corner, it shows you a little thinking, like their version of the hourglass, and we have our answer. X is 7.4999993. So basically, X is how much? 7.5. Right? X is 7.5. And then that 1096, that's 1096 what? That's the energy we use, the number of calories we spend. Is 1096, at 1096 calories, is that better than anything that we had in our table? What was the best we did in the table? The fewest number of calories was 1109. This number is better, it's lower. It's not lower by a whole heck of a lot, but it's lower. So let's go ahead and grab that answer and write it down, and then we'll interpret it. Okay, so 7.5 and 1096.875. So 7.5, 1096.875. Yes, Derek. Okay, let's take a look. Show me what you did. So let's do the calculation again. So do second calc. And then number 3. You can hit enter right now because it's definitely to the left of the answer. So just hit enter. Now you have to hit the right arrow a bunch of times until this dot gets past the bottom point. So keep going until it's definitely passed. A little more. That's good. Hit enter. Hit enter one last time when it says guess. That's it. Okay. All right. Everybody come on back here. Come on back. Come on back. Okay. So a couple of ways that we can improve on what we did and some ways that we can make a mistake. If you go into second calc and you try number 3, you don't need to do this. If I say left bound and I put the arrow right there, and then for the right bound, if I don't move it far enough, if I don't get to the right of the answer, well, it's not going to tell me, hey, you didn't move it far enough. It's going to find the best answer that's in this little tiny interval that I told it, okay? So the best answer there turns out is 6.8 and 1,134 calories, but that's not what I want. I want the best answer in the whole thing, okay? An improvement on hitting that left arrow a million times, instead of asking, like to push the left arrow a bunch of times, if you just type in a value of X, it will jump the cursor right there. It doesn't even look like it's waiting for an X, but it is. So for example, I know definitely 6 is less than the answer. So if I just hit 6, it says, okay, we'll put the cursor at 6. There it is. And I'll be like really greedy and say, okay, definitely like 12 is way past the right answer. It says, all right, cursor is 12 right there. And so I don't hit the left and right at all. I just type in 2 numbers, make sure you're on both sides of the answer. Questions on that? One thing, I don't know if you remember, but is that answer exactly the same as what I got before? Anybody have a different answer on your calculator? It wasn't a 2 before. Yeah, so you have an 8. I had a 3 before, now I have a 2. So this is not a precise, like it's not an exact type perfect kind of thing. It's going to be close enough for us, but you can see we can get slightly different answers depending on how we do it. You're not on the curve anymore. See, the cursor is just freely off of the curve. So of all the points on the curve, this is the minimum. Okay, let's try part I. We will go to Serge. Okay, can you guys give me one sentence in plain English that has both of those numbers in the problem? Write a sentence that has both numbers, plain English, not really any math. Okay, does anybody have a sentence they're willing to share? Let me see some hands. What was the end of the sentence? Fred loses the least amount of energy. At 7.5 miles per hour. We'll make sure we get the units in there. Can we tweak the sentence a little bit to include the 1096? Yeah, so the least amount of energy, and maybe we'll kind of squeeze it in right there. 1096.875 calories. Okay. So when I grade a sentence like this, I'm looking for the first number, that was the V. I'm looking for the second number, that was the E. I'm looking for the units, miles per hour, and calories. And I'm also definitely looking for what kind of a word. Least, minimum, smallest, fewest, some indication. You could write tons of sentences like this, but the specialness of that point is that it's the least number of calories. Questions on that? Okay, let's take a look. We're going to skip past J and jump down to 3. Can we go to Joe? Okay, so these are pictures from your book. If you have like a roller coaster type curve going up and down and up and down, we have names for the high points and we have names for the low points. So the high points are called local maximums, or local maxima, I guess is the plural. And the low points are local minima. And I just want to make a distinction. Is this guy right here, is that the highest point on the curve? No. So we have to put the word local in the front. We're not saying it's the absolute maximum on the curve. We're just saying locally, if you're looking only nearby, it is higher than its neighbors, right? Is this the highest point anywhere on the curve? Maybe with this window, but if I buy that this thing is doing something like that, then where's the highest point on the curve? Somewhere else. I mean, maybe there isn't one if it goes up forever, right? So it's okay. We can still use the word max, even if there are higher points somewhere. There's something interesting about those points at the top. They are locally higher than the points nearby. Same idea down below. And then one other distinction here. It says if you see the phrase local maximum value, we are talking about the y value, the height. If you see local minimum value, again, we are talking about the y value. So as a quick example, if I ask you, what is the minimum value of my energy function? Your choices are 7.5 and 1096. Which one am I talking about when I ask for the value of the function? It's the 1096. The 1096 is the minimum of all the different energies you could spend, right? Is 7.5 the minimum velocity you could go? Couldn't we go 7 or 6 or 5.1? So when we say minimum value, I know that there's like two numbers here. There's an x and there's a y. But whenever we say value, we're talking about the y value. Doesn't make sense to say 7.5 is the minimum value. Something special about 7.5 in terms of being minimum. Is that clear? You see value, it's y value. All right. And let's try number 4. We're back to Ben. Okay, so average velocity. We actually oftentimes use the letter R. We were calling these the rates when we did all those word problems way back when. Do you remember the basic equation that relates the rate and the time? Okay, so I'm going to write another version of what Iris had said. This was the equation that we started with most of the time. Rate times time is distance. Yes? And we're looking for the rate. So what do I do to both sides to solve for R? Divide by that t. Okay, so the rate is the distance divided by time. Said another way, the average velocity is the distance divided by the time. Okay, easy enough. Suppose that we look at the graph over here. And I want to focus on 2 points. I want to focus on that point right there and this point over here. First of all, this point on the right has a 4 associated with it. 4 hours into our journey, We are at the 200-mile road marker on the highway. Okay? 4 hours in, we're passing the 200-mile mark. What does this mean? 1 hour in, we are at the 50-mile mark. Let's write those two things over here. So after 4 hours, we've gone 200 miles, and after 1 hour, we have gone 50 miles. And if I asked you guys to find the average velocity over that period of time, well, let's see, it looks like we've got a distance and we've got a time. In this interval, how much distance did we cover? We covered 150. 200 minus the 50 is 150. How much time elapsed? It was 3 hours. 4 minus 1 is 3 hours. And what do we do to get the average velocity? Distance over time. So don't we have to divide these guys here? Divide these guys here. So we get 50 as our average velocity. And if we put units, then it'll actually sound like an average velocity. What were the units upstairs? It was miles. And the units down there were hours. 50 miles per hour. That sounds like an average velocity to me. Were we going 50 miles an hour the whole time during that period? No, you could see that we weren't going 50 miles an hour in the beginning, because in the beginning, this is kind of like, it's kind of a slow curve here. We're going kind of slow in the beginning, but then you can see that it gets steeper towards the end. I think we were kind of making up for lost time in the second part of the trip. So we're not saying we were going 50 miles an hour the whole time. We're just saying on average, we were going 50 miles an hour. And the last thing I want to add here is that doing this 200 minus 50 and this 4 minus 1 and dividing them should look very familiar. It looks quite like something we've done a bunch of times. Megan, what does it look like? Megan, what does it look like? It looks like a slope calculation, doesn't it? You subtract two numbers, you divide, you subtract two numbers. Is it a slope calculation? Well, let's see. That 150 is the vertical change, the rise. That 3 is the horizontal change, that's the run. 150 over 3, it's exactly a slope. And so we've got this note here at the bottom. Where are we now? We'll go to Hazen. Okay. Yeah, that's a really good question. Eliza says the slope is not, you said continuous. I'm going to say the slope is not constant. The slope is not constantly 50 miles an hour. In fact, what does it even mean to talk about the slope of something that's curvy? We know how to talk about slope of a line. In fact, the line that I was imagining is the one that connects the 2 points. So we have no trouble finding the slope of that line. It's exactly what we did. Slope of that line is 50. And so Eliza's raising a really good question that actually doesn't get answered until a calculus course, where it's really defined what the slope of a curvy thing is. I will say that that when we say slope of something curvy, we actually mean the slope of a thing called a tangent line. You guys ever seen? Raise your hand if you've seen or heard tangent line. About half of us. So a tangent line is actually a line that comes in and just barely touches the curve at that one spot. And so when we say slope of something curvy, we're really talking about slope of some tangent line that's right at that point. So you're right, it's a good observation. We're not saying it's 50 miles an hour the whole time. We're not even saying it's 50 miles an hour at any point. But on average, we were going 50 miles an hour for those 3 hours. Okay, this concept of average velocity is something we can make even more general. It doesn't have to be a distance on the vertical and a time on the horizontal. It really could be anything. And we could just think of velocity as being a rate of change. How fast is something changing? How fast is our distance changing with respect to time? And on the next page, we've got our definition. Sam? Okay, that's our definition. It's just another slope calculation. Let's try to put it in action in number 9. Megan? Okay, so let's try this. The idea here is that we're thinking of these two numbers as being A and B. Doesn't matter which one you call which. And we're going to follow our definition here. I'll abbreviate rate of change by ROC. So according to our definition, we're doing f of b. Which one is b? 5 for my example. Minus f of 2 divided by, it says b minus a, 5 minus 2. You know you're doing it right if you can kind of see same thing on the top and the bottom, just the top has f's on the numbers. All right, now there's work to do. We're supposed to find f of 5. We're supposed to find f of 2. And you guys maybe split up that work and find those two numbers. I got 4 and negative 5. Are those right? Any questions so far? So you plug in the 5 and I got 4. Plug in the 2 and I got negative 5. That's replacing those x's with 5 or 2. Hazen, you with us? Where did we lose you? So to find f of 5, we can do this. I mean, like this whole idea of function notation is really new. It's okay to be confused. If we want to find f of 5, we're saying that the x is 5. So all of these x's become 5s. So just plugged it in. Okay, on the top, 4 minus minus 5 is 9 over 3, which is 3. So the average rate of change between those 2 points on that function is 3, and that's it. In some sense, the function is changing by like 3 miles per hour between those 2 points. Eric? Did you get the f of 5 is 4 part? Okay, so we'll take a look at it. All right, so we have 25 minutes. This thinking functionally activity will take you a good chunk of time. So see if you guys can work through, check with your neighbors, take your time and really try to get your hands dirty in terms of interpreting these functions.